Imagine building a machine, sending it into the dark, and not finding out what it actually discovered until 6 years after it happened, because a single broken part meant nobody could measure it properly the first time. That's the real story hiding behind Voyager 2, and almost nobody tells it because everybody's too busy talking about its more famous twin. Stick around, because this one changes how you think about the edge of our solar system. And if you want more real space stories, subscribe now. Here's a fact that surprises most people. Voyager 2 launched first, August 20th, 1977, 16 days before Voyager 1 followed on a faster route. Despite launching second, Voyager 1 got the lower number because its path was expected to reach its targets first. That's the only reason the naming feels backwards. Voyager 1 was sent toward Jupiter and Saturn, then flung out of the solar system's plane entirely, trading any chance at the outer ice giants for a closer look at Saturn's moon Titan. Voyager 2 got a different assignment, a longer, more ambitious one. In the late 1970s, Jupiter, Saturn, Uranus, and Neptune lined up in a way that only happens once every 176 years. That alignment made something possible that had never been possible before. One single spacecraft, using each planet's gravity as a slingshot, could visit all 4 giant planets in one continuous mission. Voyager 2 took that path, and to this day, nearly 50 years later, it remains the only spacecraft in human history to have visited Jupiter, Saturn, Uranus, and Neptune. Every gas giant, every ice giant, one machine. But that longer, more complete tour came with a cost: time. Voyager 1 reached the true edge of our solar system, the Heliopause, in August 2012. Voyager 2 didn't reach that same boundary until November 5th, 2018. 6 years later, on a completely different side of the solar system. For those 6 years, Voyager 1 got all the headlines. Every discovery about interstellar space came from its instruments alone. But there was a hole in that story, a big one, and almost nobody outside the scientific community knew about it. Voyager 1's plasma science instrument, the device built to directly measure temperature, density, and flow in charged particles, had already failed. Not at the boundary, not in interstellar space. It stopped working in 1980, before Voyager 1 had even reached Jupiter. So when Voyager 1 made history crossing into interstellar space in 2012, it did so without the one instrument that mattered most for understanding what that crossing actually felt like. Scientists could infer things from other data, the cosmic ray detector, the magnetometer, but direct plasma measurements, the kind that tell you what's really happening at the boundary, simply weren't available. A 32-year gap nobody could fill. Voyager 2's plasma instrument never broke. When it crossed the Heliopause in 2018, it carried a working sensor that its twin had lost decades earlier. And what that sensor recorded became one of the most significant datasets in the mission's history. For the first time ever, a spacecraft measured the plasma on both sides of the boundary, inside the heliosphere and out in true interstellar space, at the exact moment it crossed the line between them. 5 separate research papers, published together in Nature Astronomy in November 2019, laid out what Voyager 2 actually found. And what it found didn't confirm 6 years of assumptions, it broke them. The first surprise was the shape of the boundary itself. Scientists expected something thin, a sharp line, maybe a few 100,000 miles wide, where hot solar wind met cold interstellar plasma cleanly. Instead, Voyager 2 found a transition zone, roughly 100 million miles wide, sitting just outside the boundary, in territory that was supposed to be pure interstellar space. Tendrils of interstellar material had pushed inward, mixing with the solar environment in a way no model predicted. Voyager 1 had seen something similar on its own approach, a stagnant region where the solar wind seemed to run out of momentum. But Voyager 2, crossing from a totally different direction, found a different structure entirely. Similar scale, completely different behavior. 2 spacecraft, 2 crossings, 6 years apart on opposite sides of the solar system, and 2 genuinely different pictures of the same boundary. The second surprise was even harder to explain. Both spacecraft crossed the Heliopause at almost exactly the same distance from the Sun, roughly 121 astronomical units for Voyager 1, 119 for Voyager 2. That wouldn't be strange if both crossings happened under similar conditions. They didn't. One crossing happened near solar maximum, when the Sun's activity is high and the heliosphere should theoretically expand outward. The other happened near solar minimum, when it should shrink. Instead, the boundary sat in nearly the same place both times. Scientists still don't have a solid explanation for why. The third surprise involved temperature and density. Solar wind plasma inside the heliosphere runs scorching hot, tens of millions of degrees in the particle speed sense physicists use. Researchers expected a sharp cool down at the boundary as it met the colder interstellar medium. Voyager 2 measured that drop, and it was sharper than models predicted. But the real number came from the other side. Interstellar plasma, measured directly for the first time in history, came in at roughly 30,000 to 50,000 degrees Kelvin, hot by everyday standards, but about half of what earlier theoretical estimates had guessed. And it was dense, more than 40 times denser than the solar wind at the boundary, a finding both spacecraft confirmed independently, giving scientists their first real stereo measurement of the space between stars. The fourth finding is the one that reshaped how scientists talk about the heliopause entirely. It leaks. Not metaphorically, actually leaks, in both directions. Voyager 1 detected interstellar particles pushing inward before its crossing. Voyager 2, approaching from a completely different angle, detected solar particles leaking outward before it ever reached the boundary. Two spacecraft, two different mechanisms, two different sides of the solar system, 6 years apart, and the same underlying conclusion. The heliopause isn't a wall. It behaves more like a coastline, with material washing across in both directions constantly. Now step back for a second because there's a bigger story hiding inside all of this. When mission planners chose Voyager 2's longer route back in the 1970s, using computers weaker than a modern calculator, they weren't just planning a scenic tour of the outer planets. They were deliberately avoiding the trap of relying on a single data point. One spacecraft can't tell you whether what it finds at the edge of the solar system is typical or just a fluke of where it happened to cross. Two spacecraft, approaching from different directions at different times, can actually start building a real picture. What they couldn't have planned for was which instrument would survive to make that picture possible. Voyager 2's plasma sensor, running for 4 decades in deep space radiation, while Voyager 1's failed before the Cold War even ended, wasn't something anyone could engineer in advance. It was luck, wrapped inside an extraordinary amount of endurance. Which brings us to right now, the summer of 2026. Voyager 2 currently has 3 working science instruments left. The plasma instrument that made the 2018 discoveries possible is still one of them. So is the magnetometer. So is the plasma wave subsystem. Together, these 3 are providing something nothing else in the history of astronomy has ever provided. Continuous, real-time, physical measurements of interstellar space from an object actually sitting inside it. But the power is running out. Every spacecraft launched with roughly 470 watts, generated from the slow radioactive decay of plutonium inside 3 onboard generators. That decay never stops. It costs the mission about 4 watts of power every single year, permanently. Voyager 2 currently has slightly more power margin than its twin, which is why it still has 3 working instruments while Voyager 1 is down to 2. That margin isn't large, and it keeps shrinking. So engineers are attempting something they've nicknamed the Big Bang. The plan involves swapping out several powered systems at once, turning some off entirely, replacing others with lower power alternatives, all in a single coordinated operation instead of one careful step at a time. The reason for doing it all at once comes down to risk. Mid-transition, a spacecraft sits in an unstable state between its old configuration and its new one. Those unstable states can trigger automatic fault protection, a safety system that starts shutting things down on its own if power draw exceeds what the generators can supply. The entire point of the Big Bang is minimizing time spent in that dangerous middle ground. If it works, it could extend Voyager 2's remaining instruments by at least another year, possibly more. If it doesn't, there's no second attempt. Every command takes more than 16 hours to arrive. Every response takes more than 16 hours to come back. Testing ran through May and June of 2026. If it succeeds, the same procedure gets attempted on Voyager 1 no earlier than July. So why does any of this matter, beyond the engineering drama? Because the questions Voyager 2 raised in 2019 are still completely open. Why does the heliopause sit at nearly the same distance from the Sun, no matter what the solar cycle is doing? What actually determines where that boundary lands? What's causing particles to leak across it in both directions? And does that change as the Sun moves through different parts of the galaxy? Even the overall shape of the heliosphere is still debated. Some models describe a long, comet-like tail. Others suggest something closer to spherical or even lopsided. Voyager 1 and Voyager 2 are sampling 2 single points on that structure. Every extra year either one survives adds another data point toward finally settling the question. And underneath everything sits a harder truth. There's no replacement mission. Nothing else is anywhere near interstellar space, and nothing will be for decades. When the last instrument on these two spacecraft finally goes dark, the map they've been drawing simply stops. It's worth remembering what got Voyager 2 here in the first place. It's the only spacecraft to ever visit Uranus, discovering 10 previously unknown moons and 2 new rings during its January 1986 flyby, along with a magnetic field so wildly offset from the planet's rotation axis that it still challenges how scientists model planetary magnetism. It's the only spacecraft to ever visit Neptune, finding 6 new moons in August 1989, clocking supersonic winds over 1,500 miles per hour, and capturing nitrogen geysers erupting from Neptune's frozen moon Triton, a world now believed to be a captured object from the Kuiper Belt rather than something that formed alongside Neptune at all. All of that from a spacecraft designed to last 4 years, built with technology from before the internet even existed. The team keeping both Voyagers alive in 2026 is small and getting smaller. Many of the original engineers have already retired. The people who replaced them had to learn programming languages and spacecraft systems from an era before their own careers started, just to keep talking to machines built to be spoken to in a language almost nobody uses anymore. But perhaps the most remarkable part of the Voyager story isn't how far the spacecraft have traveled. It's how much they continue to teach us, long after their original mission officially ended. Most planetary missions have a clearly defined finish line. They launch, collect their data, complete their objectives, and eventually fall silent. Voyager ignored that script decades ago. Every year it survives becomes an entirely new chapter that nobody expected to write. That's one reason scientists remain so determined to keep both spacecraft operating. They're no longer just studying planets. They're studying the boundary between our solar system and everything beyond it. That boundary isn't fixed. It's constantly changing as the solar wind pushes outward, while the interstellar medium pushes back. It's a moving frontier, one that breathes and shifts over time. The only way to truly understand those changes is through direct measurements. And right now, Voyager 1 and Voyager 2 are the only instruments humanity has positioned there. No telescope can replace them. No satellite orbiting Earth can collect the same information. The data simply can't be gathered from anywhere else. That's what makes every additional month so valuable. Scientists aren't just receiving numbers, they're building a record that future generations of researchers will still be analyzing decades from now. Some discoveries won't become fully understood until entirely new theories are developed. History has shown that often happens in science. Data collected today sometimes answers questions that haven't even been asked yet. Voyager has already done that once. Measurements taken during its flybys of Jupiter, Saturn, Uranus, and Neptune are still appearing in new scientific papers today. Researchers continue finding details that earlier generations either overlooked or couldn't fully explain. The same will almost certainly happen with the spacecraft's interstellar observations. As computing power improves and scientific models become more sophisticated, today's measurements may reveal patterns nobody currently recognizes. That's another reason preserving the mission matters. Once the spacecraft goes silent, the opportunity to expand that record disappears forever. No amount of funding can restart it. No future mission can simply pick up where Voyager left off. By the time another spacecraft eventually reaches interstellar space, decades will have passed. Conditions around the sun will have changed. The galaxy itself will have moved. It won't be the same moment in cosmic history. That's why these final years are so important. Scientists aren't simply trying to extend the mission because they can. They're trying to preserve a scientific record that can never be recreated. It's a race against a clock that never stops ticking. Every year, the generators lose a little more power. Every year, another difficult decision has to be made. Another heater switched off. Another backup system retired. Another careful calculation about what can still be kept alive. Eventually, physics wins. The plutonium will continue cooling. Electricity will continue fading. And one day, there simply won't be enough power left for another transmission. NASA already knows that day is coming. The challenge has never been avoiding it. The challenge is delaying it for as long as possible. Because every extra signal that reaches Earth is another piece of a puzzle nobody else can solve. It's remarkable to think that these spacecraft were assembled by hand. Their circuit boards inspected under magnifying glasses. Their software written on computers with only a tiny fraction of today's processing power. Yet they're still operating in one of the harshest environments imaginable. Few technologies built by humans have ever demonstrated that kind of endurance. Even fewer have continued producing meaningful scientific discoveries nearly half a century after launch. In many ways, Voyager represents the opposite of disposable technology. It was engineered carefully. maintained patiently, and adapted repeatedly whenever new challenges appeared. That philosophy may become increasingly important as humanity prepares even more ambitious missions into deep space. Future spacecraft headed toward the outer planets, or eventually toward another star, will likely spend decades traveling before reaching their destinations. The lessons learned from Voyager will help shape every one of those missions, not just in engineering, but in operations, planning, and problem-solving across generations of scientists, because that's ultimately what Voyager has become. Not just a spacecraft, not just a scientific mission, but proof that human curiosity doesn't have an expiration date. As long as there's still something left to discover, someone will keep trying to listen, and somewhere beyond the planets, far beyond the edge of the solar wind, two aging spacecraft continue drifting outward into the darkness, still carrying humanity's oldest ongoing conversation with the stars. And for now, that conversation isn't over yet. Right now, the tests are running, the commands are going out, the responses are coming back 16 hours later, and two machines the size of small cars, powered by plutonium sealed into their generators nearly 50 years ago, are still sitting out there in the dark between stars, still measuring a region of the universe no human instrument had ever directly touched before they arrived. Voyager 1 is the one most people remember. Voyager 2 is the one that actually told us what interstellar space is made of, because it happened to keep the one instrument that mattered most, working decades longer than anyone had any right to expect. If you want to know whether the Big Bang procedure succeeds, and what happens when NASA attempts the same fix on Voyager 1 in July, subscribe and turn on notifications. This is real data from real instruments, explained at the weight it actually deserves.